Time appropriate greetings, everyone, wherever you are in this world. And thanks for coming for my talk here. So today I'm going to talk about small things. And, elephant is more scared of an ant than lion. So what we're going to talk about here is size optimization. So how to create small images with Yocto project. This is one of the very outstanding feature of Yocto in general that you can leverage heavily. And I imagine that you have a new feature that you need to deliver, and you are running out of flash space, and it's difficult for you to kind of get that in without freeing up some space in there. So so these things, they hit you hard when they do hit. So it's important that you know about the constraints and you know about what we can do there. And therefore, if you're working with the Yocto project, then it's important to know that there are some constructs in there, some help in there that you can design around and get some benefits. So that's what we're going to cover today. Feel free to ask questions on IRC, and we'll get back to them if I kind of run over my time. Otherwise, I'll try to answer some of them here. So you're going to cover poky-tiny, which is the distribution policy, and then some image analysis, and then some tools, optimizations that you could utilize, and a few other tricks around metadata restructuring. So that's pretty much we're going to go. All right, so introduction here, you will see that if you look into meta poky directory, which is the distribution policy layer in the poky distribution, you will find there are 3 distribution policies in there. One of them is called poky, which is the standard default distribution. Basically, that's the default if you don't do any changes. Poky-tiny is geared towards the small size. And we'll primarily talk about that more and what it has in there, and we'll cover more of it as we go. And the third one is poky alt config. That's more of like uses systemd and LTSI kernel and so on and so forth. So somewhat different configuration than the defaults. So examples I've used are based on a derivative of poky distribution, which is essentially good. So you might find a little bit discrepancies, then let me know, but usually it should just work with poky as it is. Okay, so poky-tiny, where can you find it? What it has, so how could you do it if you customize to your own distribution? So I recommend you inherit from it, which means that you construct your distribution based off of poky-tiny. That's easier way to get started. You can also look at it, learn what is in there, and adopt whatever is suiting your requirements in there. That's a good way to get started. And I've just given a little snippet here how you could kind of have your own distribution policy that is based off of poky-tiny. Okay, so what's in poky-tiny essentially is what you will see, in the following slides. And what it does is default for poky is glibc for C library. Poky-tiny uses muscle. And so what you see here, the image size reduction that I'm showing is essentially you built the default distribution that uses systemd, and then you go down, right? So for the presentation sake, I'm showing that way, but it's easier to construct up, which means that you should lay these policies first and then add stuff. So being additive is easier, and having a small base is easier that way, but reducing an already enlarged image is a harder task because there are dependencies that show up, and there are more intricacies that you will not know when you are doing top down. So usually the approach should be bottom up for reduced sized images. So whenever you are in your design phase, know your hardware well. That's what I always tell people: know your hardware well, know its constraints, and if you are not the one who is calling the shots for your software configuration, make it aware that they know that what the constraints are. And and then obviously these are the tools that will support you in achieving what you want. Muscle is smaller in size. Obviously, you can see it saves you almost 2 meg, or not so much, maybe 1.5, but it does save you some. But there are implications because it changes your interface to Linux kernel. So know that your applications may not be ported to muscle, and we do have support in Yocto project for the packages that you'll get from uh, you know from Yocto, but you might have your own applications, and so you have to pay attention to that as well. That if um, they are kind of not ported to muscle, then there will be work involved in there. So I just want you to make a conscious decision when you go with such decisions, because they do have work entailed in them. So it shouldn't be just that, oh, let's replace glibc with muscle and life goes on. It doesn't work that way. The interfaces are different. There may be missing functionality, and you might have other issues where you have some kind of dependency on behavior or threads or some sort. And these are practical problems. Ideally, you would say that yes, an application should adhere to POSIX and be done with it, but truth is far from it. The second thing that you will see, and also in poky-tiny you will have, is the init system selection, right? So this is also very fundamental. BusyBox init is what it uses. And BusyBox, I think most of you will be familiar with, is basically your combined toolkit to get a lot of stuff done on small, tiny systems. It also offers you an init system, which is kind of cool if you are like space constrained. And so you can use BusyBox init. And the other option it has is you can use the device manager instead of using the UDAV, which comes like by default with systemd and is used with sys5 init. You can use mdev, which is again a BusyBox utility. So what you will see is that this reduces your size, but also changes your behavior. So when you are changing your init system, know that what you are signing up for, right? So you won't be able to use journal, right? The nice things about systemd. You will not have perhaps already existing init scripts for a particular application that you are bringing in, or a library or a service that you're bringing in from open source. Otherwise, you might have to write those apps or those init scripts for it, and you may not get the notification mechanisms of systemd, the other cool features. So know your system, what your end system should look like, and this could be a good option. Maybe it is not a good option for reducing your size. There are other ways that you will be able to reduce your size with other init systems too. But so this is absolutely towards how small it can go. And you can see here, once we changed to BusyBox init, the size dropped considerably. The reason there is that there are many dependencies that systemd brought with it. And going down from 35 meg to 3 meg is good. I think there was some bug in there that perhaps brought in additional dependencies. I'm not sure, but obviously you will see that the size reduces considerably when you select these options. Okay, so next, I'm going to cover some compiler stuff. And there is a global setting that we have in Yocto project called selected_optimization. You should be seeing this in your bitbake.conf file in the core layer. It is usually set to be O2, which is generally used optimization level, with few additional options that you would see here. I've given a little snippet here from bitbake.conf with relevant information, how it is constructed. As you can see, full optimization is what's feeding into it. And then it feeds into target C flags, which is used everywhere. So you could basically switch to using OS, which is optimizations for size. Generally, it should reduce your code size again further. As you can see here, it went from 3.1 to 2.9. Now, it may vary for you, right? So there is a range that you can expect depending upon what your applications are and what your image consists of. But generally, it should reduce your size quite a bit. There are a few quirks with selecting, say, optimizing for size again. It's not very commonly used in other distributions, for example. So you might run into bugs that no one else has, right? So compiler may crash. Your program may behave suboptimally. However, it is good that you know of those pitfalls, although I'm not sure you'll fall into many of those, but it is possible that you'll run into some of them. In some cases, what you would see is when you do compile with OS, the code not only gets smaller, but it also runs faster. And you would be scratching your head, why would that happen? So again, understanding the architecture is important because instruction cache that's on your CPU is very precious. And the less or the more code that is run is stored in there, better it will behave rather than you caching if else, and basically half of your cache is filled with the code that won't execute. So obviously, when you optimize for size, your fetchers or your instruction fetchers on your CPUs are basically fetching more code because it's compact. And that might result in performance improvements too. However, there can be downsides as well, like the branching may not be as good as it would be with say O2 or newer ones. So there are multiple factors that may factor in. So always measure, right? As I've shown here, measuring the size, you also want to perhaps measure your performance when you are doing this at the same time, and put some benchmarks in there that whenever you're going this way, then you can basically compare, because in the end, it is the load dependent thing, right? So everybody has a different kind of load. Your benchmarks are not my benchmarks, and vice versa. All right, so the next thing you can do with compilers, and this is relatively new, and it's the link time optimizer. So what is LTO? Link time optimizer generally is basically a whole program optimizer. So what it does is it calls so it generates intermediate code, not really object code directly. And then when you invoke the linker invokes the compiler again and provides it access to all the files that it has compiled. So as you can see, now compiler has an opportunity to look beyond the single compilation unit, right? So say you had 10 different files building your application, and usually it goes file by file, which means it only gets to see the headers of that particular file and the source code in that file. So it cannot do whole program optimizations. If there is, say, it cannot eliminate code that is a global function but isn't used anywhere, right? It has no idea. Maybe another file is using it. However, when you present all files to it, it can figure that out. That, hey, you got a global function in there, but nobody is using it, so I can eliminate it. So it's pretty cool, and it's new. And you can enable it. What I've shown here is a little snippet for compiling a core image minimal. But as you can see, it doesn't come without work, because what you can see here, I've disabled it for several packages. glibc, muscle is not there, but but you can see there is list of them. BusyBox is in there. The reason I've disabled them is they don't yet work when you enable LTO, right? So the reason is that there may be certain assumptions that are made in the source code that now compiler is being overzealous with optimizations, and then the program is not behaving well. But some of the large applications, and for example, from practical experience, Open vSwitch resulted in almost like 30% reduction in size, right? So you want to look at it as an option when you want to include like more richer packages into a smaller footprint images. Here, we didn't get much. The reason is, as you can see, most of the packages that are going to core image minimal are either disabled or they are not in the list here. There are anyway very few of them that go in there. So still, even if we had 1 or 2 packages, you see that it has saved few bytes. But if you build a fairly large image, you will see at least 5 to 10% reduction in your image size. So I'm also working on making it generally available, how we do with security flags. I think in future you might see LTO as an option that you can just include it in your configuration. But I've done an initial kind of a proposal, haven't worked on it to make it worthy for inclusion upstream yet. So watch out for that. Clang has actually support for LTO, which is much nicer. It has thin LTO and full LTO. So one of the downsides of LTO is that your compile times are a little bigger because it's calling compiler one more time. And it needs gold linker, right? And there are a few quirks in there that I ran into that gold linker, what does not work with optimization for size. So there you go. But that's a Clang problem. I think it's a bug in Clang. So it will be sorted out in GCC. It doesn't, this bug doesn't exist. So we'll see. I think, as you can see, these are certain upcoming new things that you will find in project, but you can also enable it per package. So, you don't have to enable it distro-wide. You can just choose certain packages where it will be applicable to you, and you can get like more selective benefits. So how do you look into the sizes, right? So I don't know how many of you work with Buildhistory, but what Yocto project can do is, when you're building, if you enable the Buildhistory class, it will create a separate repository in your top there, where it will store all the information about what went in the build. And that is what I'm going to cover here. So you enable it. I've kind of shown here how you would do it. Once you have enabled it, build your images, and then you would see that you will have build history created in there, and I'll cover it a little bit in further slides. So refining your images, and once you start refining your images, so here are a few things I've shown. So for example, image linguas, right? So if you don't need any locale stuff in there, you can empty it out, right? So there is default in there, but you might want to take a look at it and say, I don't really need it, remove them, right? That's going to reduce your image size further, or include the ones that really matter to your products. So pay attention to these variables and image features, right? So if you have inherited from an existing image, you might want to disable certain image features that perhaps aren't useful for your tiny images. And I've shown here splash, most of the time, say if it's a headless system, you really don't need any splash in there, remove it, right? You are doing a different way to update your system, don't have package management in there, right? So it will not have any online package management data, stuff like that. If you need SSH, choose drop bear instead of like fully blown open SSH. That will reduce your size further. Likewise, I've given a few examples here, but there will be more that you can find on those lines in image features that you can throw away, that you really don't need. For Default tunes, if you're working on ARM systems, then I highly recommend that you choose the thumb ISA, right? So there is 32-bit ISA and then there's a 16-bit ISA. That was the thumb one, but then thumb two is one that's used on new Cortex, 32-bit Cortex cores. So I've kind of shown you, if you don't know, you can look at if you're building for your device, which is an ARM device, and you see that thumb is missing in your tune features, investigate that, right? It's highly likely that, or I would say thumb would be supported on your SoC, unless like it's a very custom SoCs or where you have disabled it. But here I've shown you how you would be choosing a default tune value, right? So look, that T is in there, right? So Cortex A7, T stands for thumb, HS stands for hard float ABI, right? So have T in there, that would be the indication that you want to default to thumb instruction set. And you can see here, once I switch, this is a Raspberry Pi image that I was building, and you can see that my image size went from 3.3 meg to 2.9 meg. So that's a good amount of saving in there just by switching the ISA. And thumb ISA is default for many distribution, like Debian uses it. And so it's very well maintained and very well tested out there in the community as well. So you can be pretty sure that you won't find like a lot of issues than others. If you're doing MIPS also has 16-bit ISAs. So you could choose the 16-bit ISA. It is supported by the project. You could use that for MIPS as well. Okay, so build history. I did mention that before, how to enable it. So what I've shown here is basically I'm getting into the image, right? And just trying to show what all it contains. Just so actually similar information occurs, is there for every package that you can get. But I'm specifically getting into the image here. The image is also a recipe in the end. What you can see is it shows you the dependencies that it has, right? There's build ID. The dependencies are basically the interesting pieces that you'll look when you're optimizing for size. And there is the size information in the install package size file. So all these files are important that, when you're looking at it, pay attention to those, and you will find opportunities to do size optimizations. So when I look into my install the package sizes file, this is how you will see it will be listing. What are these packages? These are your output packages, that it is listing here. Say, if you had RPMs in a RPM as a backend, then this is the name of the RPM basically that it is showing you. It's not a single file, it's not the recipe name, but it's the output package name. So be aware of that. You have to associate it with the recipe that it is coming from. Most of the time, you'll be able to do that. But you can see here who is contributing to size. So, I've listed here like the top packages. And there you go. So you get like a lot of information about who is contributing how much, and you can kind of spend your effort accordingly. Dependencies. So once you figured out that, hey, this is something I can throw away, but how do I decouple it, right? So you could look into the .e files. If you have a good display and heavy machine, you can like plot it. Or what I do usually is I look into those files and I just look for the dependencies. So, I look for on the right-hand side, look for this arrow mark and the name of the package in quotes. And it tells me who is asking for it. And I can recurse over them and find out where I have to decouple it, right? So with kernel tweaks, you could also have some optimizations in kernel where you can reduce the kernel size as well. The ones I've shown are primarily rootfs size reduction techniques, but kernel has its own config. You could look, say, disable this, this. I don't need these many options, and you could create a configuration based on tiny config, which is available in kernel. I didn't do much with the kernel this time, but in half an hour, this is how much I could present to you guys. But it'll be interesting to see where the sizes go with all these sizes. Size optimization in kernel is a separate parameter. You might have to enable that in the inner config if you want to optimize for size. Okay, so here's a little bit of size comparison that I've published. You might want to take a look at it. It basically takes various combinations, muscle with BusyBox in it and MDAL, and then BusyBox with glibc, and then with sysvinit, with systemd and all. So you can see that the size does vary. So the smallest root FS you'll get is around 1.5 MB, right? Or maybe 1.9, but less than 2 MB for sure. And so whatever your policies are, that will be what you will use. So future work, Toybox is available as well in not in the core as of yet, but I want to experiment with that as well and see whether that's any better. And LTO, I did mention that we want to or would look into enabling it system-wide. I know that Fedora is doing too as well as of now. I don't know whether they will enable it in Fedora the next release, but there's work ongoing, so I'll share some work with them. And I'll also explore, because there are more switches than OS. For example, if you are using Clang, they call OZ. That basically optimizes even further, right? So I want to see whether there are more opportunities from the tools. And then what I've seen shown here is primarily C, C++, but we see that Go and Rust and Python and all, they are also getting into the smaller images more and more. So we want to investigate whether there are opportunities in there too. So all right, so thanks for your time. That's all I had. If you have any questions, I know I'm a minute above or over my time. If you want me to answer a few questions, I can. Otherwise, I can move back to Slack and we can continue our discussions over there.